Hello Ecotopians. Today our lecture is on geology, geology for Ecotopia. And you might wonder, geology? Geology for Ecotopia? Why geology? And the reason we're studying geology is because, well, the four classical elements are useful for understanding ecology. The four classical elements, what are they? Well, they're the earth, they are the air, they are the fire, and they are water. And those were thought to be the essential parts of the universe going way back to before the ancient Greeks. And it may seem kind of hippy-dippy-ish or paganistic or whatever to think of the four elements, earth, air, fire, and water. But I found that it's really useful in understanding ecology because much of the living world interacts continuously with earth, air, fire, and water. And so earth today we'll talk about, air being the atmosphere, and fire being the energy that flows through ecosystems, and water, of course, is extremely important to ecosystems. So we'll focus today on earth and the study of geology. So the earth gives rise to mountains and topography, and we'll talk about that giving rise to part in a moment, but just wanted to make sure you understand topography. Topography is the arrangement of features on the face of the earth, and so the position of the mountains and the rivers and the watersheds and good soils and bad soils and so on and so forth. Topography also includes man-made objects, so it's just, stuff on the earth. Mountains and topography give rise to rivers and watersheds, and so as we study the redwood ecosystem, we will be spending a pretty good amount of attention on rivers and watersheds. And rivers, of course, are hugely important in lots of ways. And watersheds are natural units of topography. More on watersheds later, but watersheds are there because of the geology of an area. Also, rocks and mountains contain minerals that affect terrestrial life. So there's certain minerals that are very important to terrestrial life. I'm thinking phosphorus and nitrate. Also things like copper and manganese and magnesium, all very important to life. And they derive, many of them derive from rocks. Also, some are very important economically, some locally important economically. Gold in cinnabar, as far as I know, there isn't much or any gold in the redwood ecosystem strictly defined, but not far outside of our redwood ecosystems we find important deposits of gold, such as in the Trinity Alps and in the Sierra Nevada. Cinnabar is a mineral from which mercury is derived, and mercury is used for purifying gold. And so those are two very important minerals. Maybe not important to us now today, but historically the presence of gold in California brought an awful lot of people and really changed the course of history in our area. So we wouldn't be what we are now without gold having been in California. So that's why I wanted to mention them. And they're found in mountains. Limestone, really important where it's found, and everywhere else where there's humans, because limestone is used to make cement. And so if you look around, won't take long before you find some concrete or cement, and that was made with limestone. So limestone is found in rocks. And then I just wanted to say something about gravel. I mean, who cares about gravel? Well, gravel is actually a really important construction material. It's used in the production of concrete. You mix cement and gravel together and you get concrete, gravel or sand. And I just wanted to show you some of our local gravel quarries, because we have some. So let's go over to, let's see, I think we're going over to, yeah, so you probably don't know where we are. Okay, this is the Eel River, just south, oops, no, I'm sorry, this is the Mad River, just near Blue Lake. And out near Hatchery Road, there's a big gravel quarry. And you can zoom down here and you can see all their equipment. And what they're doing is they're gathering, or harvesting really, gravel from the bed of the Mad River. Which they do in conjunction with oversight by the Department of Fish and Game to make sure they don't harm habitat. And you might think, whoa, what happens when the gravel is all gone? Well, it won't be gone anytime soon, because every winter it washes down out of the mountains. So it's quite an interesting resource that we have in our area. Oops, oh shoot, I got both in the same spot. I'll show you another one. It's just south of Eureka. Here it is, just south of Fortuna, where the Van Dusen River comes in. Oh boy, I'm pretty sure it's here. Yeah, it is. Okay, here's Highway 101, and right off the road here is this gravel quarry right here. And they're doing the same thing. They're harvesting gravel from the riverbed in summertime when it's low, and making it available for all the different purposes we use gravel for all kinds of construction and road building. Very important resources. Okay, back to geology. Okay, gravel, and just have to mention that rocks weather into soils, which is soils are the basis for plant growth, and redwoods are plants, and that's why we're studying geology. Okay, so let's get to it. What do we need to know about geology for Ecotopia? Okay, the big view. Take a look at the Earth. Probably all of you guys saw this when you were in kindergarten. The idea that the Earth is round and in the middle it's got this core that's molten. Actually, it's solid, surprisingly enough. Pretty darn hot, but under such great pressure from the stuff around it that it's solid, and outside it it's liquid and so on. So the Earth is a gigantic ball of mostly molten or semi-molten rock. What a fantastic idea. We can't see it. We have to trust the geologists to tell us that it's there. Because we only live on the crust up here. So we live on the very outer part. And of all the stuff on this slide, what I really want you to know is the crust, and I also want you to know just the word mantle. So the mantle is the semi-molten rock below a very thin layer, relatively thin layer of solid rock. So we live on it. And the crust comes in two forms, continental and oceanic. Now, continental is composed of lighter minerals that kind of float. An oceanic crust is made of relatively heavier minerals, which are heavier, and so they get covered with water, so they're oceanic. And we will come back to granite and basalt later when we talk about igneous rock. Okay, so we say, they say, the geologists say that the Earth has a very thin crust on the top of it. And then they say, at least for the last 50 years, they say that the surface of the Earth, the crust, is broken up into individual plates, tectonic plates, and that these over long periods of time float around and bump into each other, and sometimes they're consumed and sometimes they arise. And some of them are continental. Some of these plates have continents on them, and some of them don't. Now, this picture shows all the plates in North America. The ones that I would like you to know are the Pacific plate and the North American plate, and this itty-bitty little one here, the plate of Juan de Fuca. And we're going to take a closer look at that one because what it's doing greatly affects our lives. Here's a close-up of it that some geologists put together. It's bounded in this gray line. This is the last little bit of the plate of Juan de Fuca. And I say that because apparently it is being subducted, or it's slipping underneath the North American plate. Very slowly to us at a rate of 3.2 to almost 5 millimeters per year. A millimeter, 5 millimeters is probably half the length of your fingernail or something like that. So it's moving very slowly to us, but over hundreds of thousands and millions of years, it's pretty fast and it's being gobbled up. And as it does this, it's causing all sorts of earthquakes. Every time it moves, it doesn't move smoothly, it moves jerkily, and every jerk is an earthquake. And every earthquake that we know of has been recorded with these yellow lines. So you can see that all along the junction of this plate with the other plate is a place where there are earthquakes, and we live in earthquake country. Here's a close-up just near us. Here's Trinidad, and here's Shelter Cove. You can't even, well, you can. Yeah, Eureka is underneath all these freckles. So just off Cape Mendocino is what's called a triple junction. It's a junction of the Pacific plate, of the North American plate, and the plate of Juan de Fuca, which is sometimes known as the Gorda Plate. This little part of it is known as the Gorda Plate. And it's extremely geologically active. As of the shooting of this video earlier this week, we had a magnitude 6.9 earthquake right in this vicinity over here. It shook us enough to wake us up, didn't do any damage miraculously. A 6.9 is pretty strong, and if it were someplace else, if it had been a different kind of an earthquake, we would have had a lot of damage and probably maybe some deaths. Okay, so that's where we live. It's very active geologically. Oh, I just wanted to say, so where you have plate motion, the earth fractures, and those fractures are called fault lines. And earthquakes happen along fault lines. It's where two bits of the earth move relative to each other. And I didn't want you to leave you with the impression that all this stuff is happening offshore. A lot of it is happening onshore. And right around Eureka, in fact, throughout Humboldt County, we have a number of active faults, some of which come right through Arcata. Probably Fickle Hill is on a fault, or at the base of Fickle Hill is a fault, with one side going up and the other side going relatively down, and you get topography being formed. Yeah, so you can see all this. So the tectonic activity in our area affects our topography greatly. You see all the faults trending from the southeast to the northwest, and if you look at the way our rivers flow, our rivers also flow from the southeast to the northwest. I think the Eel River is one of the world's longest north-flowing rivers after the Nile or something like that. But so flows the Mad River, and so flows Redwood Creek, and our mountains too are in these long ranges, which are determined by this tectonic activity in our area. So that's the background on the big picture of the Earth and plate tectonics and continental drift and where we are with that. Now I just wanted to do some really brief background on what's called the life cycle of rocks. So rocks have a life cycle. They're born, they live, and they die over extremely long periods of time. You just have to trust the geologists on this. Let's just start the cycle with the igneous rocks. And an igneous rock is a rock that has solidified from a molten state. As soon as it is exposed to the atmosphere, it begins to weather. It begins to break down in a number of processes that I'll talk about in a moment. And then the broken down parts are transported, and they may be deposited, and if they're deposited in a thick enough layer, they're lithified or turned into rock. And so that initial kind of rock from weathered rock material is called sedimentary. It sediments, it's buried. If it gets buried deep enough, it may come in contact with enough heat to deform. And so if it starts to melt, if it twists and turns and is deformed, that's called metamorphic. Once it's melted, it's magma. And then from a magma state, it can crystallize either underground, in which case it's called intrusive, or it can crystallize after it's shot out at the atmosphere in a volcano, in which case it's called extrusive. So intrusive igneous rock often has very large crystals, and I'll show you that, because if a mineral cools very slowly, it can form a very large crystal. But if it's shot out and cools very quickly, then the crystal, you can hardly see the crystals at all. So we'll now go through those rocks and check them out one at a time. So the three rock types, the first is the igneous type, and what I'm showing you here is extrusive igneous. Very briefly, here's a picture of a volcano that I happened to witness firsthand in Ecuador last summer when Tungurahua erupted, and I was there. Very, very dramatic. Love to tell you about it sometime. But this is magma, and it's going to solidify and turn into rock. In Redwood Country, we do not have much extrusive igneous at all, and to my knowledge, I don't know if we have any. It's certainly not common. But if you go north to the Oregon Cascades or Washington Cascades, you'll find a lot of igneous rock. In fact, most of western Oregon, that's all it is. The Coast Range and the Cascade Mountains of Oregon is all extrusive igneous rock from what must have been enormous eruptions of magma once upon a time. And they often form these really cool shapes, and you see these here and there throughout the world. Devil's Tower is one. Devil's Post Pile, I think, is another one in California. So it's extrusive igneous rock. Intrusive igneous rock. This is from Yosemite National Park. In Yosemite National Park, in fact, most of the high Sierras is composed of granitic rock or intrusive igneous rock. So this is that again that molten rock that solidified very slowly deep underground. These guys are enjoying some of the relief up there, relief being, I guess, vertical displacement. Either that or they just happen to trip over these little rocks that someone put over there. If you look at this piece of granite here, you can see some pink spots and some white spots and some black spots. And these are actually different minerals that have crystallized. So these are individual crystals that solidified over very long periods of time, deep underground, after which they were then uplifted by tectonic activity and mountain building and exposed up here for us to see. So all this stuff here was once a gigantic blob of molten rock underground, which solidified and then was uplifted, and anything that was on top of it has eroded and disappeared, and now we get to enjoy it. It's a fascinating story. All right, second type, sedimentary. So this is sandstone. If you take enough sand and bury it deep enough, it'll get hot and under pressure, and it'll just start to solidify from sand into sandstone. And if you do the same thing with mud, mud turns into mudstone, and silt turns into siltstone. So you get all kinds of different sedimentary rocks. And if you ever have a question about that, you can just look around here and eventually you'll find some sedimentary rock, very young sedimentary rock with looks like clamshells in it. So yeah, sedimentary rock. So this must have been sand with or mud with these shellfish in it, and it just got buried so deep this stuff never got broken up or decomposed or whatever, and it's turning into a fossil. And just a fantastic story. This is Mount Everest, and I have heard that at the very tippy top of Mount Everest there are clamshells, that the rock there is sedimentary rock, but it's been uplifted by the collision of the Indian subcontinent with the Eurasian continent or plate, and uplifted, and so there's seashells composing the rock of Mount Everest. Fascinating story. Third rock type is metamorphic, and so just to remind you, so metamorphic rock is when some other kind of rock, it could be sedimentary, it could be igneous, that is solidified, then comes into contact with something hot enough to melt it very slowly under long periods of time. This couple inches of maybe sedimentary rock may have taken 1,000,000 years to deform like this. So it just becomes a little bit like taffy, and over long periods of time it just changes. Metamorphosis is a change, that's why it's called that. So it's been altered by its contact under high heat and pressure. So the three rock types, igneous, sedimentary, and metamorphic. Know them, please. Once that rock has been exposed through mountain building, immediately it begins to weather. So there's different processes of weathering, and I'm just really don't have the time, it's not the place to get into it, but briefly, this rock here is being exposed to physical weathering, and probably what happened is it had tiny little cracks in it that water worked its way into, and water, when it freezes, expands greatly with great force, enough to actually crack rock. So that's what's happened to this guy here. Another way that weathering happens is through biological activity. So this would be chemical weathering. So these lichens that crust on this rock produce acids, and over long periods of time those acids eat away at the rock, and some things dissolve away, and that which is resistant stays behind, and so you get a sorting of the chemicals. I took this picture of this red soil in coastal South Carolina, and it's an extremely old ancient soil that has been heavily weathered by warm temperatures, high humidity, and long periods of time. Anything that could be dissolved out of that soil has dissolved, and what's left behind is very high in iron and aluminum, and it just gives the soil this red color. It's a very ancient, highly weathered soil. So in this one picture we go from brand new rock full of all kinds of minerals to this ancient weathered rock, which is now soil, and has a very different chemical composition from its parent material. So weathering, it happens. Takes a long time though. Once it's weathered, it is then subject to erosion and transportation. So probably you know what erosion is. There's natural erosion and there's erosion that's accelerated by human activity. Once soil moves or rocks move, once they're broken away from the parent material, they can be transported. And this picture in the Himalayas from Google Earth shows these glaciers, which are weathering the rock and then transporting it downstream. And I just want to show you some Google Earth images of erosion and transportation in our own backyard. Here's one. Let's see, what is it? This takes us to the Kings Range. The Kings Range is just offshore. Okay, so here's Whitethorn and Shelter Cove, and up north is Eureka. And the Kings Range just jumps straight out of the ocean. It's being uplifted pretty rapidly, and you can see that it's eroding into these watersheds. Here's great big slide areas, and all this stuff slides down. It gets 200 inches of rain a year, and so that stuff is transported, the eroded material is transported downstream, and you can see it accumulating in the valley bottoms. And over the years, the braided river changes course and pushes all this gravel out to sea, where it's picked up by the oceanic currents, and the heavier stuff goes to the bottom and the lighter stuff gets pushed around. And you can actually, Google Earth is so fantastic, it lets you see underneath the water. Is it going to let me do it? Not in this view for some reason, but you can change the settings and you can actually see underneath the water. Actually you can see all kinds of things. These braided channels underneath the water are actual canyons that probably formed when the ocean level was much lower during the ice ages, when all the water was locked up in the ice caps. And so you can see former transportation patterns underwater. Fascinating stuff. Another sample of erosion and transportation. Oh, forget that. Been there already. Here's another one. Just up, this is Highway 299, just up out of Blue Lake. And if you've driven that, you know every now and then the road gets all wobbly and womply. It's because the road is going over an area that's geologically unstable, and it gives the highway engineers fits because the ground is moving underneath their road, and it makes the road all bumpy, and sometimes it gets wiped out altogether. What you can see here is this whole area here is probably a former slide. They built the road here. It's unstable. It tends to drop rocks and mud down. They're continuously pushing it off and cleaning it and trying to stabilize it. They cut a little road in here to capture whatever falls down or prevent more slides. So that's really common in our area. Here's another place. Anywhere you want to see what's called mass wasting or landslides, just look for a squiggly road. That's a road that's going up a steep area and doing switchbacks. And this looks like this is an old logging road, a really bad one that just was sort of cut and abandoned. And this is area where we're getting landslides from the road building, and you can just follow this road along and just see how it's wasting away, and that's erosion that gets into the rivers and is really bad for fish. I just wanted to show you, looking around, you find all sorts of interesting things. Check out this grow scene. Look at these guys. I was looking for landslides, and I thought these were landslides, and I zoomed in, and all I see are really huge greenhouses. But that's neither here nor there. Anyway, let's go to the one last example of erosion and transportation. Sorry about that. And just outside of Rio Dell, as you take Highway 101 south and you look across the Eel River, on the other side is a great example of just a steep river cut. So the river cut this, maybe accelerated a little bit by an old railroad or road, and it's just eroding directly into the river. The Eel River has one of the highest rates of natural erosion of any watershed in the world, and that's because it's in the Franciscan melange, and we'll talk more about that in a moment. Okay, back to our slideshow. The Franciscan melange. This is a cross section of California. So we have the Pacific plate, or here is called the Farallon plate, being subducted, and the Great Valley is the Central Valley of California, and here's the Sierra Nevada, the granitic Sierra Nevada. And what happens is all this stuff is part of the North American plate, and it's been moving in this direction and scraping off anything on any plate that is subducting. This stuff gets scraped off and then incorporated into the land. So the coast ranges of California, from about Big Sur to north of us, has all been scraped up off the ocean floor, and it's a mess. It's a chaotic assemblage of all kinds of different rocks. Here's just a very poor picture that shows off the shore, looking onshore, this huge block of rock and some other kinds of rock, and it just shows how mixed up and jumbled it is. If it were all sedimentary, you'd see lots of parallel lines. If it were all granitic, it would look just like basalt, but it's very heterogeneous. All kinds of different rock types mixed together because in the process of being scraped off the ocean floor, it's been turned and twisted and faulted and jumbled together. One of the things it gives us is just absolutely beautiful beaches and rivers because all these different rocks have been eroded from the Franciscan melange and transported south. So here they are. I did want to say something about this green rock. It's called serpentine, and I'm not going to say much about it in this lecture, but if you want to have a good read about a certain kind of rock that's in our area, read about serpentine. It's serpent as in snakeskin, snake, and it's just fascinating, but I'm not going to say more about it now. So in summary, that's all the geology I wanted to cover, and I'm just showing you this map to remind you of where Redwood Country is, and now you can think of this whole area in a new sort of way. It's on the edge of the North American plate. It's composed muchly of Franciscan melange. It's fascinating stuff. Plate tectonics gives rise to topography. We live in a very geologically active place. There's active mountain building in Redwood Country. The mountains affect the local climate. We'll say more about climate soon. We have earthquakes, landslides, and whitewater rivers because of all this stuff. Rocks weather away and they erode and they become soil or sediment. Minerals cycle between the crust and the mantle. That's the rock cycle thing. Rocks cycle from igneous to sedimentary and sometimes metamorphic. And natural erosion is very rapid here and is worsened by human activities. And the Franciscan melange is a chaotic assemblage of rocks. That's the material we covered in this lecture. I hope you enjoyed it, and we'll be seeing you soon. Take care.